says record. All right. So, screen share. And here we've got, let's see, here's Q1. We, and you guys did some of this without me, of course. Starting with matter, you all know elements, compounds, and mixtures. Remember that elements are made of one thing. Compounds are two or more that are in a fixed ratio. So the ratio is always the same. That's why we can use that little percent to mass, mass to mole, divide by small, multiply to whole when we do the empirical formulas, because that percentage is always fixed for a compound. And then mixtures, of course, hang on, I'm rearranging this, are not fixed. So if you want to separate an element, you can't, because it's only one thing. If you want to separate a compound, you use chemical changes, because you have new things forming. And if you want to separate a mixture, you use physical changes, because you're just separating the substances. They're still the same substances. Okay, and you guys did a lab where you had salt and sand, and you dissolved the salt and the sugar, and then filtered out the sand. And I think that was about the last thing you did before I came back. So, if I remember right. All right, questions about elements, compounds, and mixtures? Probably not. All right, atomic structure. For once, he didn't put any, do you need me? No, okay. He didn't put any questions about, you know, what was Rutherford's model or anything like that. That usually there's a question on there about that. But you guys all know, if we're talking about an element, the proton number is down at the left-hand corner. The mass number is the top left corner. The top right corner is going to be the charge. And if you remember, so this is protons plus neutrons, and the charge is protons minus electrons. So if you're given a mass and a proton, you can easily figure out how many neutrons you have, because you just take mass minus protons. And if you're given protons and neutrons, you can figure the mass, obviously, by adding them together. And then charges, the number of protons minus number of electrons, and that's going to be when we're talking about ions. So that's pretty basic. We talked about isotopes. Isotopes, I don't even think there was an isotope question on there. Oh yeah, there is an isotope question. All right, isotopes are when you have the same element with different masses. And you find the average, but in order to find the average, you have to add up the percent of each isotope times its mass. And then divide by 100. For instance, I should have had an example. Let's say that this is totally made up. Carbon 12 is 90%. So you would take 90% times 12. Carbon 14 is 9%, so you would take 9 times 14, and carbon 13 is 1%. So you would do the multiplication of all those, add them up, divide by 100. And your answer should be somewhere between 12 and 14, and it's going to be closer to 12 because that's the predominant isotope. Okay, does that make sense? Hopefully. Let's see, electrons. The electrons, if it's neutral, the protons are going to equal the electrons. And the electrons, remember that they live in different places. I'll send you guys a hotel chart that you can print out if you want. If we were in class, I'd give you one. But let's recall how the electrons situate. If this is our nucleus, you have the first energy level, which has an S room. The second energy level has an S room and then 3 P rooms. The third energy level has an S room, 3 P rooms, and then it has 5 D rooms, but those 5 D rooms don't fill until the 4S room does, because of energy level. I'm going to move this down so I have a little more space. Maybe. All right. So then we get 2, 3, 4, 5, the D levels. All right. This is one level. This is one level. That is all on the same level. And 4S would be in a different level. It would then go 4P. And then you would go 5S and so on and so forth. Okay, you don't have to go to anything that extreme though. So that's the first rule. And when we talk about quantum numbers, we have the energy level is the N number. So if you were to see something that said NP, that tells you that the N is just a substitute for which energy level. So something that's in 3P would be up here in one of these 3. Something that's in 2P would be in one of these 3. The N is just a substitute for a level. So if you talk about alkali metals, they all have, let's see, hydrogen isn't a metal, but it has 1s electron. Who's next? Lithium has 1s, 2p. No, we don't have p levels. We just have 1s2, 2s2. Two S1. So, and if we did sodium, it'd be 1s2, 2s2, 2p6, 3s1, right? So they all end in s1. So one way of saying that is the alkali metals all have this electron configuration. N meaning which energy level they in, but they all end in s1. The alkaline earth metals all end in s2. And that's one way you can figure out things about the periodic table. Okay. So back to filling. The rules for filling electrons is we start with the lowest energy first, and then we build up. So if we want to do phosphorus, phosphorus has 15 protons. So when he's neutral, he's going to have 15 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we would write that 1s2, 2s2, 2p6, 3s2, 3p3. Okay. Notice that I didn't double up here. I spread them out because that's more stable. Now, we learned when we talked about periodic table that all atoms want to be like the noble gases, which mean they all want to have an outer shell full. So right now, if we've got phosphorus, if he wants to bond with somebody, he's going to bond in order to get 3 more electrons. And those electrons would fit in here. So if we figured out what phosphorus's electron configuration is, now it's 1s2, 2s2, 2p6, 3s2, 3p6. This would be phosphorus with a -3 charge. That's a neutral phosphorus. So if you have a question about an ion and it says, what's the electron configuration of sodium? You have to go back and figure out sodium's electron configuration when he's an ion. And sodium's in the first family, they're going to lose 1 electron. So that's going to be sodium's ions electron configuration. Okay? So, basic rules on electron configurations. Now, quantum numbers. The quantum number is just our way of identifying what particular electron we're talking about. All right, there's 4 numbers. There's the N number, there's the S number. The S number is the shape. A round S orbital has a number of 1. A p orbital, S orbitals are 0. P orbitals are 1. D orbitals are 2s, and F orbitals are 3s. So if I wanted to talk about this particular electron, he's in the 2nd energy level, so his N number is 2, and he's in an S orbital, so his S number is 0. If I want to talk about that guy, he's in the 3rd level, and his S number is a 1. And S stands for secondary principal number, and N stands for primary principal number. Okay? So, electron or quantum numbers. The 3rd one is which particular electron we're talking about, and it's the oh, this is not S, it's L. Gosh, sorry guys. That's L, not S. So this is going to tell us which hotel room that electron's in. So let's go back to the first one we did. This guy here, he's in the S hotel room. There's only 1. So his ML number is also 0. This guy that we did, he's in the 3rd orbital. We call the first one -0, the second one 0, the 3rd one +1. So he's going to be 3. Oh, here's his numbers: 3, 1, 1. All right. This guy right here would be 3, 1, -1. All right. The last number is the shape. So ML is the particular hotel room. The last number is the shape, or the spin, which means either up or down. This guy here is up, so he's going to be a +1/2. This guy's up, so he's going to be a +1/2. This guy was down, so he's going to be a -1/2. Okay? So you end up being able to identify which exact orbital or electron you're talking about, because you have the primary number, which energy level he's in, the L number, which is his shape, which tells you whether he's s orbital, p orbital, or d orbital, or f. The ML, M sub L, which tells you where he is in orientation. So look at my picture here. If we're talking about p orbitals are this shape, but you have one on the x-axis, one on the y-axis, and one on the z-axis. And that is what we're talking about. This is the -1, this is the 0, and this is the +1. So that's why we have to differentiate between them. And then the final is whether they're sleeping up or down. And that's the spin. All right, so I'm going to stop there for a moment and take questions about electrons and quantum numbers. And I'm also going to make sure nobody else has tried to come in. I'm going to come out here just so I can check. Nope, it's still us. So you guys have a question?
I think I'm good so far.
Okay, Brooklyn?
I'm good.
All right. So then the other topic with electrons is the energy involved in them. And I actually wrote a grant. I'm waiting for Mr. Herman to send me a letter of support. I'm going to try to get more of those energy sources. This is when we put the rainbow glasses on and looked at the tubes of gas. Okay. We know that electrons behave as a wave, but they also behave as a particle. And Heisenberg is the guy that came up with the uncertainty principle. Which says the electron is either going to act as a wave or act as a particle. Sorry. The idea here is that you can either know how fast the electron is moving or you can know where it is, but you can't know both. So if you know where it is, you will have no idea how fast it's moving. If you know, or how fast it's oscillating. If you know how fast it's oscillating, you don't know where it is. And that's the uncertainty principle, okay? So when you talk about electrons, the electrons, I'm gonna go back to another drawing. We've got each of these levels and the orbitals are within the levels. If you get an electron and you excite it, it's going to move if it gets the right amount of energy. And the energy it gets is called a quantum of energy. It takes one quantum to move it. And it depends on which orbital it's moving to, how much energy it takes. It's going to take more energy to go from 1 to 3 than it does from 1 to 2. But it's not going to ever go 1 to 2.5. It has to make the exact, it has to land on the energy level. If it doesn't land on the energy level, it doesn't go anywhere. It stays put, okay? That energy can be calculated if you know how fast the electron is waving back and forth, the frequency of it, and you have to know what's called Planck's constant. Now, a constant is something that is going to stay the same no matter what calculation. And Planck, because they named the constant after him, duh. Planck is the one that figured out that the more energy something has, the higher the frequency is going to be. And the Planck's constant is just the way to change it. Just like if I know I have 1 inch and I want to figure out what that is in centimeters, I have to multiply it by 2.54 because there's 2.54 centimeters in 1 inch. Planck's constant is just multiplying the frequency to get the energy, okay? How do we calculate frequency? Well, because that guy acts as a wave and a particle, we can measure his wavelength. And if we had the right kind of rainbow glasses in the lab, we could have done that. Instead, we did a worksheet that went along with it that told you what the wavelengths were for hydrogen. But we know that the speed of light is equal to the wavelength, which has the upside down Y designation, times the frequency, which is the little funky little v designation. Speed of light's always constant. It's 3 times 10 to the 8th meters per second. So wavelength times frequency is going to equal the speed of light. And now you can solve for either frequency or wavelength given whatever you're given. If you need to do energy and you're given wavelength, first you're going to have to figure out frequency, and then you have to plug frequency into energy. So energy would be equal to the speed of light, which we use the letter C for, divided by wavelength, because speed of light divided by wavelength is going to be frequency, times Planck's constant. And that'll be given to you, 6.63 times 10 to the negative 34th joule seconds. And like I said, that'll be given to you. So that's what this is, all this math is. Now, once an electron gets excited, he's going to fall back at some point. And when he falls back, he is going to release that energy, and we call that energy package a photon. This is where the energy acts kind of like a particle. It is released vibrating, but it can act like a particle too. And that is, we call a photon. So, questions about that?
Nope.
Nope. All right. Density and significant digits, figures. Density is just algebra. Density is equal to mass times divided by volume. We did that the very first week of school when we did the golf ball lab. What gets kids is when you have to solve for this. Now you got to rearrange it. All right. To rearrange it, multiply both sides times V. Now, if we're still solving for volume, he's not by himself yet. So now we got to divide both sides by D. So volume is equal to mass divided by density. And I don't know if I gave you this because I wasn't there, but no, this is mass, volume, and density. You can use this little mnemonic. So if I'm solving for mass, I'm solving for volume, I cover up volume, I have to do mass divided by density. If I'm solving for mass, I'm going to multiply volume times density. And if I'm solving for density, I take mass divided by volume. Okay, there's a density question on there, and it's solving for volume. I'm just going to tell you right now. Also, significant digits. All we're talking about with significant digits is if we measure something and we have a ruler and we have a line right there, and this is 1 inch, and this is, or not 1 inch, 1 centimeter is 2 centimeters, so this would be 1.5. So we can measure this in 1.1, 1.2, that's kind of in between 2 and 3. So we say 1.2 something. That third number is estimated, and so those are significant digits. Now, if you estimate 255, you can't estimate that well because you have to have the graduation above it. So that's what we're talking about with significant figures for measurement purposes. Now, if we're talking about numbers, here's the United States, very badly drawn. Here's the Atlantic Ocean, which has a hurricane in it. Here's the Pacific. Okay, if I give you a number, it has a decimal in it. We start, if the decimal is present, we start from the Pacific side. So I start counting at the first non-zero. 1, 2, 3, 4. That has 4 significant digits. If I give you this number, there is no decimal. So we start counting from the Atlantic side, and we start counting at the first non-zero number. 1, 2, 3. Okay, what that's saying is that when we measured this, we weren't precise enough to give us a value for the ones place. We could only give a value to the tenths place. Okay, but up here, whatever our measuring device was, it was accurate enough to go to 10th, 100th, 1000th places. Okay. When you add two numbers, that second number is really precise. But we can't, if we add them up, we can't be more precise than the least precise number. 4, 5, 6. So we have to drop those 3 off. And we would round that 7 to an 8. We have to drop those 3 off. So when you're adding, you go to the smallest number of decimal places. But when you're multiplying, you go ahead and multiply the whole thing out. And let me calculate that. 1.25 times 3.1245. 0.905625. The least number of significant figures in this was 3. So we have to go to 3 significant figures. Because that 5 is a 5 or greater, the number there for that answer would be 3.91. Okay, so when you're multiplying, you use the least number of significant figures. When you're adding, you use the least number of decimals. I think that pretty much sums up first quarter. I've got moles on second quarter, so we'll do that tomorrow. So, what kind of questions do you have now? Anything?
Nothing at the moment. This is going to be a video, right?
Yeah, it's recording.
That'll help.
Okay. If you guys, see if this will work because I'm on Zoom. I never know what's going to work and what's not. When you go to the course, on Friday, I'll put the final on the assignments. Are either of you going to have a problem with taking the final on Friday?
No, I should be good.
All right. Is 1 o'clock still good time for that?
1 o'clock Friday.
Uh-huh.
Did it just take like an hour probably?
You have 2 hours, but it's 50 questions. Are you a fast test taker or a slow test taker?
Just whatever the average time is usually what
It says the average time is 63 minutes.
Okay.
So, all right. Down here at the bottom of the assigned videos, there is, I just changed some of them, so it's actually not at the bottom anymore. Can you see where my cursor is going back and forth here?
Yeah.
If you go through those and practice, they don't line up with our quarter 1, quarter 2, but if you go through those and practice, that will be useful. That will help you.
Okay.
Okay. All right. Anything else that you can
That's
think
it for me.
You're good?
I'm good.
How about you, Brooklyn? You good?
I'm good.
Okay. So is 1 o'clock good tomorrow for another review? And is the review helpful?
Yeah, it's helpful.
Yeah.
And 1 work.
All right. So we'll go with 1. And if something comes up, let me know.
Sounds good.
Okay.
All right. Well, if you guys don't have any questions, we can be done and you can go back to bed.
All right.
Or go eat or whatever it is you do.
Yeah.
I think I'm going to go out and plant some flowers. So,
Ooh.
yeah.
What kind do you have?
I brought home a flat of impatiens from the horticulture class. and
Ooh.
they've finally started getting bigger. So I'm going to they're all in, like 6 in one pot. So I'm going to take 3 out and move them to a different pot.
That'd be nice.
So they're under my tree. So they're in the shade. They can't be on the deck yet because my husband's rebuilding the deck.
All
So-
right.
But that's where they're living right now. And oh my gosh, you should see my tomato plants. They look awesome. And they're going to
That's
have
good.
to get transplanted. And I'm going to have to go get pots for those, but we'll deal with that when that happens. So, all right, kiddos, stay safe, make good decisions, and I'll see you tomorrow.
We will.
All right, bye.
Bye.